Welcome back to a new video to introduce the topic of this week. We're going to move away from sampling schemes and we're going to focus on methodology to estimate ratios. And the second part of the material for this week is going to use this idea of estimating ratios to potentially improve the efficiency of estimators for the mean and totals, and then extend this idea using a regression technique. Again, another improvement on the efficiency of estimators. So you'll be reading chapter 7 from the textbook. Okay, so in the first part of the material, you're going to look at the problem of estimating a ratio of two means. So suppose that there's this quantity in the population that is defined by the ratio of the means of two variables x and variable y, and you want to estimate this capital R. So the obvious estimator would be to use the sample averages and obtain the ratio of the variable of the observed values for variable x and variable y. Also notice that in simple random sampling, the ratio of the sample means x and y is equal to the sum of x in the sample divided by the sum of y in the sample, and also the ratio of the total estimate in the population of x and the total sum of y in the population. And it's easy to see this if you look at the formulas of each one of these quantities. There are these scalars involving the sample size and also the population size, but they are the same in the numerator and the denominator, so they end up cancelling out, and all these ratios are equivalent. Now, there is not a closed form solution for the variance of this estimator R, but there's an approximation that is given by this expression for the standard error of the estimator R, and it involves these quantities Vx and Vy, and also the correlation between x and y. And these Vx and Vy are called coefficients of variation, and it involves the standard deviation of x divided by the mean of x, and the same thing for y, and then plus the finite population correction. This approximation works well if this condition here is verified. Okay, this condition also involves the coefficient of variation of y. You have here the standard deviation of y divided by the mean of y. So if this condition is verified, it has been shown that this approximation works well. So there's nothing very exciting about this. It's just an estimator for a ratio and its standard error. But before moving to the second part of the material, where we use this idea to improve estimators, let me just guide you through an example which I think is a nice application of the use of ratios of two quantities. This example is taken out of the Levy and Lemshaw book. It's based on exercise 710, and the idea here is that we want to estimate the incidence rate of HIV seroconversion among first-time blood donors. And there's a total of 175 donors that were seronegative, and a sample of 60 of these donors are then followed up and tested for HIV later in the follow-up. And if you look at the table of the exercise, it gives you a summary of the follow-up and the incidence of HIV. Based on that table, I've constructed a data set that you can obtain in the dataset folder of the learning website, and this dataset that I created, basically it's individual entries. So each one of these rows represents one patient, and the first rows are the 3 months follow-up, and we can see that the first two patients tested positive for HIV, and then the rest tested negative. So I do this for the 60 patients in the sample. These 60 patients out of 175. And based on this sample, I want to estimate the incidence rate of HIV positive. So I'm going to do this using SAS. I also have the code for Stata in the next slide. So first we import the dataset HIV, and then I'm going to create the weights. If we assume that this is a simple random sampling, the weights are just given by the total of the population, 175 divided by 60. And I'm also going to convert the follow-up time. Instead of months, I'm going to convert it to years. And now I'm going to use the proc survey means to compute the ratio of the total HIV status variable, that is going to give me the total number of new cases divided by the sum of years, which is going to give me the total person years of follow-up. Okay, and this ratio is going to be exactly the incidence rate. And if we run this code, we obtain an incidence rate of 0.34 persons year in this population. So this is the estimate for the incidence rate. We can do the same thing with stata. We're going to use now the SVY ratio, and we obtain exactly the same answer than we obtained with the SAS. In the second part of material, you're going to study how to use the ratio approach to improve estimators of the mean or the total or the proportions. I'm just going to give you the intuition behind it, and the intuition is fairly simple. So imagine that we have this estimator, the usual estimator for the total sum in the population. So I have this x prime, and now I'm going to assume that we have another variable y, and we know the total in the population, so capital Y. A new estimator for the total sum of the population, x prime prime, so it's going to be another estimator for the total sum, but I'm going to call it now x prime prime, can be obtained by multiplying the usual estimator and times this ratio. Or looking at this in a different way, x prime divided by y prime, which is just the ratio that we've seen in the previous slides. Okay, so this new estimator is going to be the ratio times the total of y. And under certain circumstances, we can show that this estimator, this x prime prime, is better than x prime. And why is that? Well, the intuition behind it is if you have a variable y that is correlated with x, you can imagine that you have some extra information in the data. So if you know the total of y and you have an estimator for this quantity y, by looking at how far the estimator of y is from the value in the population, you can use this information to say something about how far the x prime is from the total x. Okay, so basically if y and x are correlated, you can use the information in y to sort of correct, to adjust the value of x prime. And the resulting estimator, if the correlation is strong, it's going to have a smaller variance than the usual estimator. Okay. The other detail that is important is that despite having less variance, we're going to increase the bias. So the previous estimator x prime is unbiased. This x prime prime is going to have usually a small, but it's going to have a bias. So basically we are trading bias for variance. Okay. Finally, we're going to extend this idea of having extra information in a correlated variable, and we are going to construct another estimator, x prime prime prime, using a similar idea but extending it, because if x and y are correlated, we can actually do a regression of x and y and obtain the strength of the relation between x and y expressed in the slope b, and then use the slope b from the regression to construct this estimator, again using the usual estimator of the total sum of x, and now somehow correcting it using the information in y. So try to complete the exercises, and as always, let me know if you have any question.